Hello my dear students. So I'm going to continue the lesson. In the previous chapter, we discussed the equilibrium of an object under two forces that act in the opposite direction. So you all can remember the two forces have to be collinear, or they need to have the same line of action. They should be in the opposite direction, and also they need to have the same magnitude. And with that, we also discussed that there are different instances. There can be three forces or more than three forces under which an object is in equilibrium. So, in that sense, we will look at the second instance, that is equilibrium of a body under three coplanar parallel forces. You are familiar with coplanar parallel forces. What are they? All the forces have to be on the same plane for them to be coplanar forces. And when the line of actions are different and parallel to each other, we call them parallel forces. So, if you look at this example, in the picture you can see a bunch of bananas hanging from a rod, a light rod. And the rod also has been suspended by two strings there. And here you can see in the middle the bunch of bananas is hanging from the middle. So, what are the forces that act on this particular system? You are familiar, there is a weight that has to act downwards, the weight of the bunch of bananas. Now, if there was no rod or the strings, obviously you know the bunch will come down or it will fall down. But here it is in equilibrium. How is that possible? There has to be a force acting opposite to this. So, in this situation, there are two forces acting in the opposite direction. I am sure you all can guess what that is. The tension acting on the two strings. So, here it is the tension. Normally, we use the letter T, and W is the weight. So, here the weight is one force acting downwards. There are two forces. There are tension acting on both the strings and they are acting upwards. And if you look at all three forces, they are parallel to each other. If we denote these diagrammatically, this is the smooth light rod, and here this is the weight of the bunch of bananas, and there are two strings acting. So, this is where the weight is, and on the two strings there is the tension. So, what happens here? The resultant of the tension acting upwards, because there are two forces, they usually get added up. Why? They are in the same direction. They will be equal to the magnitude of weight and in the opposite direction. So, then the system will be in equilibrium. I am sure you all can understand this instance. With that, students, I will move on to the next slide. Another example. You all can see here a rod resting on two supports. So, these are the supports. The support. So, what happens there? The weight obviously acts downwards, the weight of the rod. That will be balanced by the reaction exerted by the support. What is that called? The normal reaction or the perpendicular reaction. Why? These are two surfaces. The rod and the support are two surfaces. When there are two surfaces in contact with each other, one surface will exert a force against the other, perpendicular to the other. That is why we call it the perpendicular reaction or the normal reaction. So, there are reactions acting in the opposite direction. Reaction, and here also a reaction. So, here you can see, students, the weight is acting downwards. There is a reaction exerted by the support on both ends. So, they will be two forces acting upwards and the weight acting downwards. So, as you can see, this is also going to be three parallel forces that are coplanar because all the forces are on the same plane. So what will happen? The sum of the reactions will be equal in magnitude to the weight of the object. So the sum of reaction exerted by the two supports is equal to the weight of the rod in magnitude. Therefore, the resultant is 0 and the system is in equilibrium. So that is this example. In the previous example also, when there was a bunch of banana hanging from that rod, the tension acting on the two strings were in the upward direction and the sum of the tension will be equal and opposite to the weight of the bunch of bananas. So those are two instances where there is equilibrium under three coplanar parallel forces. So with that, students, I will move on to the next slide. Here we discuss an activity. Investigate the factors that affect the equilibrium of three parallel and coplanar forces. So we are going to investigate the factors that affect the equilibrium of three parallel and coplanar forces. So to do that, we need this material. The first one, we need balances. We actually need two balances. So Newton balances. We need two, and we need a meter ruler, and also we need rubber bands. So we need two Newton balances, a meter ruler, and we need rubber bands. And students, in this activity, although it's not specified here, when I will be doing the activity, I will need to attach a small strip of wood to the meter ruler in order to increase the weight of the meter ruler so that we can get the readings more clearly. So I'll explain to you all how we are going to do this activity. This is the method. You can look at the diagram here. So here you can see this is the meter ruler and that weight of the meter ruler will act downwards when you suspend it using the rubber bands. So here the two rubber bands are attached to the meter ruler at the two ends. So we have to make sure that we put the rubber bands at the correct marks. Let's say if we put it at the 1 centimeter mark, on the other side also we have to put the rubber band at the 99 centimeter mark so that it is hung uniformly from both the ends. And then what we do is we attach the Newton spring balances to the rubber band, and the Newton spring balances have to be suspended from a support. So normally you all can use a stand. What we have in the lab, you can hang the balance from one stand on this side and the second stand on the other side, and that can be attached to the rubber bands, and the rubber bands can be used to suspend the meter ruler. That is how we do the activity. Once we do that, we have to observe the Newton balance readings. So before doing that, what we do is we need to measure the weight of the meter ruler. Normally, all know students, the meter rulers are light. So what we need to do is when we do the activity, if we want to get a better, higher reading, So that we can easily get the reading, what we can do is we can attach another strip of wood to the meter ruler. That will not make a difference as long as the strip of wood is uniform, and also you have to attach it in a correct manner. So during the activity, I will use a strip of wood attached with the meter ruler in order to increase the weight of the meter ruler. So then, this is how we do the activity. Measure the weight of the meter ruler. So that's going to be the first step. Once we measure the weight of the meter ruler, then only we suspend it in this manner. Suspend it at the two ends with the aid of the rubber bands and balancers, and keep the meter ruler in equilibrium in a horizontal position. So here you can see it is in a horizontal position, and the Newton balancers also have to be suspended. To do that, we use the stands. So we fix the Newton balancers to the stands, then the rubber bands are attached to the Newton balancers, and the meter ruler is hung from the rubber bands. Take measurements of the two spring balancers. The system is now in equilibrium under the action of three parallel coplanar forces. So once you do this, once the meter ruler is suspended, you all can see it is in equilibrium at a horizontal position. It's a horizontal position and it is at rest, so there is equilibrium, and during that instance, the system is in equilibrium under the action of three parallel coplanar forces. What are the coplanar forces? The tension acting on the two rubber bands, that is what we read using the two Newton balancers as F1 and F2, and there is the weight acting downwards, weight of the meter ruler. So we have already measured the weight of the meter ruler. We can read the Newton balance reading, so we can get F1 and F2, and then we can find the relationship between the three forces. Investigate the relationship between the measurements of the two spring balancers and the weight of the meter ruler. So the relationship between F1, F2 and W, that is what we have to identify. Try to push the meter ruler in a horizontal plane with a force applied normal to the meter ruler at one end of the ruler and still maintain equilibrium. So we try to push this meter ruler by applying a force from one of the ends. It can be either this end or the other end. It does not matter. While you push it, you try to observe whether there is equilibrium. So then also you have to look at the Newton balance readings. Then you will understand the conditions that need to be satisfied in order for the object to be under equilibrium under the influence of three coplanar parallel forces. So that is the activity, students. Now let's go to the lab and do this activity. Okay, students. So now we are going to observe the equilibrium of an object under three coplanar parallel forces. So you all know what coplanar is. All the forces have to be on the same plane. And parallel, if you take the line of action of the forces, they have to be parallel to each other. So for this activity, now here you can see I have two stands and the Newton balancers hanging from the two stands. And also I have a ruler here. We were supposed to use only the meter ruler, but the weight of the meter ruler was very less. So to increase the weight a little bit, I have attached another small wooden plank here that you can see. So then what we are going to do is, I have measured the weight of this wooden plank as well. It is to 300 grams, that is 3 Newton. So then, now I have two rubber bands here. What we need to do is, we need to put the two rubber bands to two ends. Now here I am putting it at the 99 centimeter mark. The same way I will be putting it to the 1 centimeter mark here. So 1 centimeter from this side and 1 centimeter from this end. After that, we have to suspend the ruler from both the Newton balancers. So what will happen? The weight of the meter ruler will act downwards, that is in the middle, and the tensions acting along the rubber bands will be upwards. all three forces have to be parallel. That is what we need to observe. And also you have to look at the reading of the balances in order to understand whether the sum of these two forces are equal to the weight of this ruler as well as this particular plank. So here I am going to hang it from both sides. Right. Now we will have to allow it to come to equilibrium. So students, can you all see the two readings? You all can see that the Newton balance here shows 1.5 Newton and the balance here again shows 1.5 Newton. So the total value is 3 Newtons and that is equal to 300 grams. So as I told you all before, the weight of the ruler with the thin wooden plank attached to it is 300 grams or 3 Newtons. So now you all can understand the weight of the object acts downwards from the center downwards, and here the two forces, so that is the tension and that is what you read in the Newton balance. So sum of these two forces is equal to the third force. All three are parallel, this one and the other force, and the sum of these two forces that are acting upwards is equal to the force that is acting downwards. So now can you all understand the concept? I will repeat that again to you all students. You can see the Newton balances are there and the rubber bands attached to it. So the weight of the object acts downwards, that is one line of action, and the two other lines of action are from the Newton balances. They are acting upwards, and the sum of the two Newton balance reading the upward forces is equal to 3 Newtons, that is equal to the downward force. So these are three parallel coplanar forces and the object is at equilibrium. Now let's say we push this object like this towards the side. From one end, if we push it to a side, you can see there is a movement. At that time, you might see there is a slight change in the Newton balance. But once it settles down again, it will come to equilibrium. So still it is the same reading. Even if we push the object downwards, again it moves up and comes back to equilibrium. So whatever the movement you try to do, still it comes back to equilibrium. That is when the three forces are parallel and in the same plane. So three coplanar parallel forces and the object is at rest. So that means there is equilibrium of forces. Is that clear to you all students? So from this activity, you all can understand when an object is at equilibrium under three coplanar parallel forces, two forces have to be in one direction, the third force has to be in the opposite direction, and the sum of the two forces that are acting in the same direction will be equal to the third force acting in the opposite direction. So those are the three coplanar forces. Okay, students. So did you all observe the activity clearly? Yes. What was the weight of the meter ruler? I told you all it is 300 grams. So when you convert it to newtons, it's 3 newtons. And then when we had the meter ruler in equilibrium, what were the readings of the Newton balances? Both read 1.5 Newton. So you all know the relationship now. If you add the two 1.5 Newton forces, that will be equal to 3 Newton. So obviously the weight of the meter ruler is 3 Newton. The tension acting on the two rubber bands, the sum of them is equal to 3 Newtons. So they are opposite and equal in magnitude. So therefore there is equilibrium in the object. That is, the meter ruler was at rest. So that was our observation. So here we can say weight of meter ruler, Three Newton. Newton balance reading F1 was equal to F2 and they were equal to 1.5 Newton. And what happened when we tried to push the meter ruler? We could not get the equilibrium. When there was equilibrium, this was how we got the reading. The two balances showed equal values. But when we tried to push it, there was no proper equilibrium. Until it was at rest, the readings were different. So here we can say, when the ruler was moving, the readings were different. So only when the meter ruler was at rest, you got the equal reading and there was equilibrium. So from that, students, what can we conclude? What can we conclude from this activity? We can say, for an object to be in equilibrium under the action of three coplanar parallel forces, the sum of the two forces acting in the same direction should be equal to the third force. So that is what we got from here. So F1 plus F2, that was equal to 1.5 Newton plus 1.5 Newton, that is equal to 3 Newton. That was equal to the weight of the meter ruler. So here we can conclude and say, for an object to be in equilibrium under three coplanar parallel forces, the sum of the two forces acting in the same direction should be equal to the third force in the opposite direction. So that is the condition that need to be satisfied. So from the observation, students, we saw that the meter ruler was 3 Newton in weight and the forces F1 and F2 were equal and they were equal to 1.5 Newton. So from that we can get the relationship like this. F1 plus F2 was equal to weight. So there, when we tried to move the meter ruler, we could not get the proper equilibrium. Why? The meter ruler was moving. Then there is no rest, there is no equilibrium. So from that, we came to the conclusion, for an object to be in equilibrium under three coplanar parallel forces, the sum of the two forces acting in the same direction, that was the upward direction, should be equal to the third force in the opposite direction. So the weight was the third force that was acting downwards. So that is the condition that needs to be satisfied. I am sure you all can understand that clearly. With that, students, I will move on to the next slide. So that is, for an object to maintain equilibrium under the action of three parallel forces, the following conditions must be satisfied. So here the three forces must be coplanar. So they have to be all on the same plane. one force must have a direction opposite to the other two forces. So like in the activity, the tension on the rubber bands were in the same direction, whereas the weight was in the opposite direction. The resultant of any two forces must be equal in magnitude and opposite in direction to the third force. So if we denote this in a diagrammatic manner, you have a line like this. Then there are parallel forces. So here you can see they are all coplanar. These are all coplanar forces on the same plane, and you can see two forces have direction opposite of the third force. And when you take the resultant, if you take this as F1, F2 and this as weight, F1 plus F2, that is the resultant of any two forces. Any two forces must be equal to the third force, that is weight. Then only there will be equilibrium. So in this instance that we saw in the previous activity, all these conditions are satisfied. The same thing goes for the example. Where we had the bunch of bananas hanging from a rod, suspended from a rod, or the light pole, a uniform pole supported by two supports. In all those two instances also, these three conditions were satisfied. All the forces were coplanar, two forces are opposite in direction to the third force, and the resultant of the two forces is equal to the third force. Then only the object will be in equilibrium. I am sure you all can understand that, students. With that, I will move on to the next slide. This is another example for three coplanar parallel forces under which an object is at equilibrium. Here, of course, this is a child sitting on a swing. And if the child is at rest, if the swing is not moving, then if you look at the forces acting on the swing, you can see what is W, that is denoted downwards. It is the weight of the child as well as the wooden plank. So the child is sitting on the wooden plank. So that weight as well as the weight of the child together will act downwards. That is one force. Then what are the other two forces? What is marked as F1 and F2? What are they? Those are the tension. So F1 and F2, they are the tension. So F1 plus F2. In order to satisfy the conditions, you can see here W is in one direction, F1 and F2, they are in the opposite direction. They are all coplanar, they are all on the same plane. And the third condition, sum of the two forces, here we take F1 and F2, why? They are the ones acting in the same direction. They should be equal to the third force, that is W. So then the resultant will be 0 and the system will be in equilibrium. I am sure you all can understand that. And normally, students, the plank of wood will have a weight and the child also has a weight. Both of them act downwards. And when the plank of wood is horizontal, so then what will happen is the two tensions F1 and F2 will usually be equal. Otherwise, you would have seen in some instances, the plank will be at an angle. Then, of course, the tension can be different. But normally, in an instance like this, F1 and F2 will be equal to each other. They will act in one direction. The weight of the child with the swing will be downwards, that is in the opposite direction. They are all coplanar, parallel. So, the system is in equilibrium. So, for example, students, if we take the weight of the boy as 500 Newton. So, F1 plus F2 will also be equal to 500 Newton. So, that means if F1 and F2 are equal, as I told you all, when this is horizontal, normally we use the same rope. So, there is no other difference. Therefore, F1 and F2 have to be equal. Then, of course, F1 will be equal to F2 and that will be half the value as the weight of this system. Is that clear to you all? So using that relationship, you all can do calculations as well. For example, if W is equal to 500 Newton and F1 equals F2, then F1 plus F2 equals W, that is equal to 500 Newton. So we will take this as 2F equals 500 Newton. So F will be 250 Newton. So that is equal to tension. If these information are given to you, you can calculate the tension acting on the room. So I am sure you all can understand this. With that, students, I will move on to the next slide. Equilibrium of a body under three forces that are not parallel. So here, this is another instance where there are three forces. They are coplanar, but they are not parallel. You have seen this type of examples. Maybe a picture or a chart or a wall paper that you make something, or even a periodic table hanging in your classroom. So here you can see this is the picture. The weight of the picture will always act downwards, and when you tie a string like this, one string tied and it is hung from a nail, you can see there is tension acting on the string. So W is the weight of the picture and there is tension on this string. But they are not parallel. Still the system is in equilibrium. So we will try to understand the conditions that need to be satisfied in order for this system to be in equilibrium. Already you know that these are coplanar forces, but they are not parallel. We will try to understand the condition that is required for the system to be in equilibrium. To do that, we will do this activity. Find out the factors necessary to maintain equilibrium in a system of three forces that are coplanar but not parallel to one another. So, two conditions are given to you. The forces are coplanar and they are not parallel to one another. So, how do they reach or achieve equilibrium? That is what we are trying to find out. So, for that we need these following materials. We need a lamina. When we say lamina, it is a thin sheet or a piece or a block or a sheet that is uniform. So, here we can use a sheet of metal, a piece of cardboard. It has to be rectangle as well as it has to be uniform. That is one material that we need, and then we need this string. We can use string or twine. Also, we will need a pencil or a marker pen in order to draw lines on the lamina. So, this is how we will be doing the activity. So, this is the method. What we will do is, first we will have to suspend the lamina. So, most probably we can use a piece of cardboard or a thin sheet of metal sheet. So, anything is fine. What we need to do is, we need to make a hole at one of the positions there. So, here the hole has to be at this point. So, then what we do is, we tie the string to through the hole and we suspend the lamina like shown in the diagram. And after that, when the lamina comes to rest, what we do is, we draw this line. Then, we need to change the position. So, now as you can see, the second position, the hole is made somewhere here and then the lamina is suspended from that point. And then, when the lamina comes to rest, again we draw this second line. So, here you can see both the lines intersect each other. Then in the third instance, again we change the position of the lamina. So here you can see we put a hole somewhere here, and then at this point we put a hole here, and then we need to suspend the lamina as shown in the diagram. There also we let it to come to equilibrium. It should not be moving. Once it is at rest, we draw the line. So here you can see all three lines intersect each other. And what is that point called? You are familiar with that. It is the center of gravity. So center of gravity is the point at which the whole weight of a body may be considered to act. If you take the lamina, the weight of the lamina will be concentrated or will act at this point. So that is the center of gravity. So in the first part of the activity, we find the center of gravity. I will go through the steps of that part. You may use a thin sheet of metal or a piece of cardboard as the lamina. So as I told you, a thin sheet of metal or a piece of cardboard as the lamina. Hang your lamina from 3 points, one at a time as shown, and mark the vertical line that goes along the string on the lamina each time. So we need to mark the vertical line. Those are the 3 lines shown there. The point of intersection. So the point of intersection of the 3 lines can be considered as the center of gravity of the lamina. Center of gravity of the lamina. Center of gravity is the point at which the whole weight of a body may be considered to act. Therefore, the weight of the lamina acts along the vertical line that goes through its center of gravity. So, when you have the lamina this way, the weight will act along this line. Why? This line goes through the center of gravity. In this instance, it's going to be this line, and in the third instance, it's going to be that line. So, depending on how you suspend the lamina, the center of gravity will act at the same point, but the line through which the weight acts will be that particular line, depending on the way you suspend the lamina. So, after we do that, we will move on to the second part of the activity, where you hang the lamina from 2 points simultaneously. So, we will look at that method. Hang the lamina using 2 strings connected to it. So, here this is important. 2 strings connected to it as the frame picture and keep it in equilibrium in a vertical plane. So, we need to hang the lamina from 2 points. Let's say if this is the lamina, then what we can do is we can make 2 holes like that, and then we need to observe. Mark the lines of each string on a sheet kept behind the lamina. So, behind this lamina, we need to have a white sheet of paper that would be easy to draw the line, and then we need to mark the vertical line passing through the center of gravity as well. So, mark the lines of each string. We need to mark these 2 lines kept behind the lamina, and mark also the vertical line passing through the center of gravity. So, when the lamina is hanging, the vertical line that passes through the center of gravity, all those have to be marked. All 3 lines marked above will lie on the same plane, and they will pass through a common point. Now, keeping the position of one of the 3 forces fixed, turn the lamina to change the plane of the other forces. You will observe that the system remains in equilibrium only after readjusting the lines of action of the forces to have all 3 forces lying on the same plane. So, in this part, what we need to do is we need to keep the position of one of the 3 forces fixed, and then we need to turn the lamina to change the plane of the other forces. So, now the plane of the lamina is this. We need to tilt it. We need to change the plane. Maybe we can have it horizontally or at an angle, and we need to observe whether we can achieve equilibrium. So that is the activity. I am sure students you all can understand the activity clearly. So we will go to the lab and do the activity now. Okay students. So now we are going to illustrate the factors necessary to maintain an object under equilibrium under the action of three coplanar forces that are not parallel. So do the activity, we need a lamina. When we say lamina, it can be a metal sheet like this or else it can be a cardboard. That is very even so that you can hang it like this and you can find the center of gravity first. Then you use that to find the way the three forces that are not parallel acting on the particular lamina. So start the activity. I have made 3 holes here. You can see here one, another one, and the other one is going to be this point. So I will be hanging the lamina from those 3 points individually, and when it comes to equilibrium, when it is hanging like this, if we place a ruler along the line of the thread, we will get a straight line. Like that, we can draw the lines and you will see how they intersect each other. So here students, you can see along this twine string, you can see there will be a line. So to get that line, we will have to hold the roller like this and get the lamina to come to equilibrium. And then if you place the roller, so now you can see string, so we will have to draw the lines there. So this is going to be one line, you can see here. Then what we will be doing is, we will have to remove the twine and then I will have to tie it at a different point. So do this again. We will have to find the line of action. Again, if I hold the ruler like this, you can see this is going to be the line of action. So that's the second line. Then again, I will have to remove the lamina. So again, we will tie another twine. So we will have to tie it like that and again and allow it to come to equilibrium. So then again I will have to hold the ruler through this point. So here you can see it's in equilibrium and draw the line there. If we draw a line through that point, so here you can see all the 3 lines intersect through the same point. At And what do we call that point? That is called the center of gravity. So when you draw very thin lines, you can see the exact intersection. Now I have used the marker pen. So that is the center of gravity. We expect the weight of the object to act in that point. So that is what we call as the center of gravity. Now that we have found the center of gravity, what we will do is we will have to tie this lamina at 2 points, at 2 ends, and then we will need to hang it like a picture hanging on the wall. So we will need to tie it from these points. So we will have to hang the lamina sheet here. So these are the two forces, the tension acting along the strings. So then I will need to use another sheet of paper. Now what I will need to do is I will have to mark the two forces. So in front and mark the points from this side and here. So this is how I got the points. Then I will have to draw the lines along the two strings. These are the two strings, two tension. Here you can see if I hold it this way, and here you have you all can see students, this is the center of gravity. So if we draw another line along the center of gravity, you can see that also will intersect these two forces. So as you can see here students, from the diagram, the two end tension acting along the string and the weight that is going to act downwards. So this is the weight that's going to act downwards and the tension acting upwards. All of them meet at the same point. So all of them are coplanar forces. As you can see, they are not parallel and also they all meet at one point. Those are the criteria that needs to be satisfied. In addition to that, you all will know that the sum of two forces will be equal to the third force. So those are the conditions that need to be satisfied in order to make an object under equilibrium under the action of three coplanar forces that are not parallel. Okay, students. So, did you all observe the activity clearly? Yes. At the beginning of the activity, we found the center of gravity. So, that was the observation we got by hanging the lamina in three different positions. So, this was the lamina. We got three broken lines cutting across or intersecting each other. And this point is the center of gravity. After that, what did we do? We hung the lamina, we suspended the lamina like the picture using two twines from two different points. So there, we had the lamina hanging like this. So there were two holes and we had the lamina hanging from 2 points. 2 points. Then what did we do? We used the sheet of paper. So we use that white sheet of paper to mark the points. What were the points? Now we had the weight acting downwards like that, and you were able to see there were two lines crossing like that. So this was the weight. Why? That is the line going through the center of gravity, and these are the lines along the two twines. So what are those forces? The tension acting on the twine. So this is T and this is also T, tension. What can you observe there? All three forces pass through this point. So here all three forces pass along this point, along one point. So that is the condition that has to be satisfied. You all saw that all the three forces are on the same plane. So during the third part of the activity, what did we do? We kept one force at the same position and tried to change the plane of the other two forces. Did we get the object under equilibrium? No. So that did not happen. So from that you can understand all three forces have to be on the same plane. They have to be coplanar forces. So then the third part of the activity, the object, or here it is the lamina, does not come to equilibrium when the plane of two forces are changed. So that does not happen. So from all these students, we can reach the conclusion. So first thing, center of gravity, that is of course something that you know, that is not a conclusion. That is to identify the center of gravity so that we know the line through which the weight of the lamina will act. So from this part, here we can see all three forces intersect each other, and also here also you can see they are all on the same plane. And also from this part of the activity we can confirm that they all have to be on the same plane. If two forces or at least one force is changed to another plane, then there will be no equilibrium like this. So they have to be on the same plane, coplanar forces. So from all these observations, students, we can come to these conclusions. One thing, all three forces must be on the same plane. That is, they have to be coplanar forces. And also, all three forces must act along one point of action. So, they will intersect each other at one point. So, then only the object will be in equilibrium. So, that is the conclusion that we can get. All three forces must be on the same plane. The line of action of all three forces will intersect each other at one point. So those are the conditions that need to be satisfied. There is one more. The resultant of two forces should be equal in magnitude to the third force and will have the opposite direction. That is also another condition that needs to be satisfied. So from all these, all three forces must be on the same plane and the line of action of all the three forces will intersect each other at one point, and also the sum of two forces will be equal in magnitude to the third force and in the opposite direction. So those are all the three conditions that need to be satisfied in order for an object to be in equilibrium under three coplanar forces that are not parallel. So I am sure you all can understand that now. With that, students, I will move on to the next slide. That is, for a system of three non-parallel forces to be in equilibrium, the three forces must be coplanar. The lines of action of the three forces must meet at a common point, and the resultant of any two of the forces should be equal to the third force in magnitude and opposite in direction. So if we take the example, this was the picture that we discussed previously. So here when we have the picture hanging like this, these two forces, they are going to be the tension and the weight is downwards. If you take the sum of the two tension, T1 and T2, the resultant of T1 and T2 will be equal to W. So if you take any two forces, the resultant of those two forces will be equal to the third force. Or if you take T2 and W, the resultant of those two forces will be equal in magnitude to T1. Then only the object will be in equilibrium. So I am sure, students, you all can understand this concept as well. So far we have discussed three different instances. Equilibrium of an object under two forces. So they have to be collinear, they have to act in the opposite direction, and they have to have the same magnitude. Then we looked at an instance where there were three coplanar parallel forces. So two forces acting up and one force acting down. The sum of the two forces acting upwards will be equal to the resultant of that. That will be equal and opposite to the force that is acting downwards. So here we have the instance where we have three coplanar forces but non-parallel. They are not parallel. So this is how that happens. So with that, students, I will move on to the next topic where we look at an instance where there are many forces acting on an object or in a system. Equilibrium can exist under the action of more than three forces. Figure below shows a system in equilibrium under 5 forces. So there are 5 forces. So you all can look at this figure. What are the forces? As you can see, this is a swing with 4 strings attached to it, 4 ropes holding it from all 4 corners. So here the weight of the string. So downwards is the weight that is marked as W. And then what is the force acting upwards along the rope or the string? That is going to be the tension, T. So here, students, you all can see the weight of the swing is acting downwards, or the plank of wood is acting downwards, and the tension acts upwards along the ropes. So it shows a plank of wood suspended by 4 strings attached to the 4 corners. So that is what you see in the diagram. The plank of wood maintains equilibrium So here there is equilibrium since its weight acting vertically downwards is balanced by the forces of tension exerted by the 4 strings. So the weight is downwards, all the tension is upwards. If you take the resultant of all the 4 tension acting along the 4 ropes or the strings, they will balance the weight. So because of that, the system will be in equilibrium. This is an example where there are 5 forces acting on the system. What else can you think of? You can think of a child or a person sitting on a chair. The chair has 4 legs. So then there is the weight of the person with the chair acting downwards, and all the 4 points where the legs touch the ground, there is reaction, perpendicular reaction acting along there. So there will be 4 forces acting upwards, and the weight of the chair with the person will be downwards. So there again there are 5 forces. So there also the system is in equilibrium under 5 forces. So here I'll write that as an example. A person sitting on a chair. That is another example. Or if you take a large table with 4 legs, there also the weight of the table acts downwards, the reaction, perpendicular reaction along the 4 legs upwards. So there are 5 forces acting on that system. So there is equilibrium under 5 forces. So like this you can think of many examples. With that, students, I have come to the end of this chapter. We discussed the different instances as I mentioned before also. 2 forces, then 3 forces which are parallel, 3 forces which are not parallel, and now here 5 forces. So in all instances, you all need to understand the conditions that need to be satisfied in order for the system to be in equilibrium. So with that, students, I will move on to the summary of the lesson. The summary. If the magnitudes of 2 collinear forces applied on an object are equal and they have opposite directions, then the object is in equilibrium. So when there are 2 collinear forces, the same line of action and they are opposite in direction, if their magnitudes are equal, the object will be at rest or in equilibrium. So that was the first instance we discussed, like an object hanging on a string or book kept on a table. All those are examples for this first instance. The second one, an object under 3 parallel forces is in equilibrium if one force is equal in magnitude to the resultant of the other 2 forces and it is in the opposite direction. So when there are 3 parallel coplanar forces acting, the resultant of 2 forces should be equal and opposite to the third force. Equal in magnitude and opposite in direction. Then again there will be equilibrium. The example is shown to you here. So as I told you all before, the tension, if it was something hanging from a certain surface, then of course these 2 would have been the tension. Here of course they have shown the diagram like this. This is one force acting towards this direction, 20 Newton. Here there are 2 forces in the opposite direction. If you take the resultant of these 2, since they are in the same direction and parallel, it gets added up. So there is 20 Newton. So the resultant of these 2 is going to be 20 Newton. Towards this direction also 20 Newton. So again there will be equilibrium. Then the next point. If an object stays in equilibrium under 3 forces that are not parallel. So here 3 forces that are not parallel to one another when the resultant of any two of the forces is equal in magnitude and opposite in direction to the other force, then of course the object will be in equilibrium. So here they are not parallel but they are coplanar. There are three forces. Then again the resultant of any two forces is equal in magnitude and opposite in direction to the other force. That is the third instance that we discussed in this lesson. I will move on to the next slide. So that is shown in this diagram. You all can see, students, A and B, two forces. Resultant of the two forces will be like this in that direction. That will be equal in magnitude to C and it will be in the opposite direction. So then again the system will be in equilibrium. I am sure you all can understand that. When the resultant of the two forces A and B is applied in the direction of the force C, the three forces will be in equilibrium. So that is the system here. Then we have the last one, even under the action of more than three forces. So more than three forces, a system can remain in equilibrium by applying forces appropriately. We looked at two examples, a plank of wood suspended by 4 strings. So the weight downwards and the tension along the 4 strings acting upwards. So there were 5 forces. Then I told you all a chair, a table, a person sitting on a chair, or an object kept on a table, a large object along with the table. If you consider, then of course through the legs of the table or the chair, there is perpendicular reaction acting upwards and the weight of the table or the chair will be downwards. So there again there are 5 forces. So these are all different instances that you see in your day-to-day life. And during these instances, if there is equilibrium, you all should be able to identify what type of forces are acting in that system. Whether there are 2 collinear forces in the opposite direction, 3 coplanar parallel forces, or 3 coplanar non-parallel forces, or more than 3 forces. That is what you have to understand mainly from this lesson. So I am sure you all have a good understanding of the lesson. So in the next chapter, I will discuss the questions from your textbook and thereafter I will discuss some extra questions.